Okay, so for the first one, so let f be given be the function given by that. On which of the following open intervals is f continuous? Okay, so these aren't points; these are intervals, right? This is like from x equals -2 to -1, but not including -2 or -1. That's why they've got the parentheses. Really, most functions are continuous everywhere except at certain x values, at least on their domain. And so for this one, I think we'll just figure out the points that it's discontinuous and then find an interval that doesn't contain any of those values. So if you don't care what type of discontinuity it is, if it's a fraction, and each kind of piece, each kind of factor on its own is kind of continuous. These are all just polynomials. If they were ln functions or something like that, they would have another discontinuity on their own, but these are all kind of on their own continuous. So really, when you have a fraction like this, just really want to know where the bottom equals 0. That'll be where the whole function's discontinuous. And so just set the bottom equal to 0. And here we'll just set each factor equal to 0. Okay, square root 3, square root both sides, but if you square root a square, if you have a step where you had to square root both sides, then this is plus and minus. And then let's just say that that is about, let me see real quick. I think let's just say it's about 1.7. Okay, and that's plus or minus. And then the other factor, set that equal to 0. So x is -0.5. So we're just looking for the interval that doesn't contain -0.5 and doesn't contain plus or minus 1.7. And so, that'll be, that contains negative. The first, for A, that interval contains -1.7. B, that contains -0.5. D contains 1.7. So C is the right answer. So that doesn't contain, the interval from 0 to 1 doesn't contain any of these discontinuities here. So, okay, next one. Okay, and I know that last one was a calculator question, but we didn't really need a calculator for that one. So, okay, so next one, number 2. Okay, so they give you some piecewise function, e to the bx when x is less than or equal to 2, and then 1.5x plus b when x is greater than 2. Okay, they say let f be the function defined above. For what value of b is f continuous at x equals 2? Okay. Okay, nice thing is you see that it's like less than or equal to. It's got the equal to here. So we know that the function at 2 is just plugging in 2. But really the function from, if you do limit, let's do that. So let's say we do, we want to show that it's continuous. So we want to make sure that the limits from left and right equal. And then they equal whatever the function equals at that x value. So we'll do limit as x approaches 2 from the left. Okay, and that's just plugging in 2 and to the bottom, and to the top one, since left is less than x. Do that. Okay, so plug in 2 for x, and you get e to the 2b. Okay. And then this also happens to be f of 2 is e to the 2b. Okay. So if we look at limit, x approaches 2 from the right. So right value is greater than 2, so we'll plug in 2 in for x here. So you get 3 plus b. Okay, and then in order for this to be continuous, whatever the limit equals from the left and right have to equal each other. Okay, so now we have this equation that we have to solve for b. Okay, so here we'll use the calculator for this one. Okay, so let's take a look at the calculator. So poof. Okay, so we'll finish off. We want to basically solve this equation in the calculator. And whenever you want to solve an equation, put one side in y1, put the other side in y2, or any of the y's, and then we'll calculate intersection. And the x-coordinate of the intersection is that value of b that makes both sides equal. Okay, so if we go to, let me make this a little bigger. Okay, so if we go, so let's look. So the first thing is to go to y equals. Okay, type in the left-hand side. You can only do x, so you can't do b. Kind of messed up when I was doing this earlier. So do e to the 2x really. Okay, put that in 1, and then in y2. Put 3 plus x. Okay, and then we'll do second trace, which is calc. And then just hit 5 for intersect, because we want to find intersection. Okay, so notice there's 2 intersection points. So notice the 2 intersection points. There's one here to the left and one here. You can only calculate one at a time. Okay, but right away we know there's 2 intersections, so there's going to be 2 answers. So it's either going to be C or D. Okay, so let's see how to calculate intersection. So basically, you're just going to move this cursor close to the intersection point, the first intersection point that you want. I'm going to move it close to here. And then really, you're just going to hit enter 3 times. It'll say first curve, second curve, guess. So right here, it says first curve. After you hit enter again, it's going to say second curve. And then after you hit enter again, it's going to say guess. But just hit enter 3 times once you get close to the intersection point. The only times that this kind of stuff matters, first curve, second curve, guess, is when there's more than 2 curves. So if there's only 2 curves, just move the cursor close to the intersection and hit enter 3 times. So notice I'm going to move the cursor. You can only go left and right when you have to. So go left and close and just enter, enter, enter. And notice that x-coordinate, and then we can write it down. So just paying attention just to the x-coordinate. That's negative 2.998. Okay. Let's find the other one. So just do second trace again. That'll be calc, and then go down to 5 again. And then we'll calculate the other intersection point. Okay, so hit enter, enter, enter. Boom, and then that's the other intersection point. So 0.646. Oh, 6.47. Okay, and then now we can see this is answer choice D. Oops. Okay, yeah, so now you know anytime you want to solve an equation in the calculator, just put one side in y1, one side in y2, calculate intersection, and it's the x-coordinate, that's the answer. Next one. Okay, so we have another calculator one. We'll need a calculator for this one for sure. Okay, so they say let f be the function given by f of x equals x plus tan x over 5 minus 10. So some kind of weird function that's got x and tan x in it. Okay, they say the intermediate value theorem applies to f on the closed interval from 12 to 15 inclusive guarantees a solution in that interval to which of the following equations. Okay, so intermediate value theorem says is if you look at the interval and if you basically plug in the endpoints of the interval into the function to get the y values, it says that the function will equal all y values in between those y values. So basically we're going to find f of 12 just by plugging in 12 into that, and we're going to find f of 15. And whatever these two y values are of this function at 12 and 15, we know that the function has to pass through every y value in between these. So if this was like 10 and this was 20, the function would have to pass through every y value in between 10 and 20. Or you could say the function would have to equal any y value in between 10 and 20. Okay, so let's figure out what these y values are by plugging this into the calculator. And I'm going to do it like a certain way, but there's like 10 different ways to do this. Okay, so let's pull up the calculator. Poof. Okay, so let's look at the calculator. And I'll do this a certain way, but yeah, there's definitely a bunch of ways to do this. Okay, so let's look at this. So first thing I'm going to do, if I have to plug in multiple values into the same function, and it's a long function like that, I'll always put the function in y equals first, and then you'll see kind of how the rest works. So first thing is just putting that function into y1. So to create a fraction, hit alpha, and then the button next to it. See, that creates a fraction. So 5, get out of the denominator, hit right. Okay, so first thing is put the function into y equals, and then we'll go to a blank screen, and then second quit. Okay, and then the next thing is if you hit alpha, the green button, and then F4, it'll bring up all the options of all those different y1s, y2, y3s. So here, so let's see, we'll type that and then that, F4. And then notice you've got all these y's. If you have a function in y8 or something, you can grab y8. And what these are is really, here, let's look at like the next thing once you hit enter. Okay, so if you do y1 and then open parentheses and then 12, so this is like almost like f of 12, you know? So this is kind of the name of the function, and this is you plugging in a number into that function. So when you put a function into y1 and then do open parentheses and a number, it plugs this number into that function, just like f of 12 would plug in 12 into f. So that's the same idea. Okay, and then just hit enter, gives you that. And then now you can go up and just highlight that, hit enter to bring it back down, and then just edit it and change that 12 to a 15 so you don't have to go back through the whole thing. And that's it. Okay, so those are the y values that we're looking for. So I'll kind of write down at least, so f of 12 is 1.084. So I should be better about, we should really round to the thousands just for practice, but the other one is 4.857. Okay, so by the intermediate value theorem, on the interval from 12 to 15, between that x value and that x value, somewhere on that interval, the function has to equal every, equal or pass through every y value in between this and this. So notice the only y value that's in between those is 4. So 4 is the only number that's guaranteed to be a solution. F of x equals 4 is a solution, or there is a solution to this in this interval. Just really means that this function passes through this y value at some point. This number 4, next one. So this has a graph already. They say the graph of the function f is shown above. On which of the following intervals is f continuous? Okay, so it's similar to the first one where we'll find all the points that it's discontinuous and then pick an interval that just doesn't contain any of those discontinuous points. So if it doesn't contain any points of discontinuity, then it's continuous on that interval. So let's find all the points of discontinuity. So it looks like, here, looks like there's a vertical asymptote, so an infinite discontinuity, and that's around 0.5 maybe. So I'm just kind of collecting all the points of discontinuity. So discontinuous at x equals, let's say, about 0.5. Okay, there's a hole here, so it's discontinuous at maybe 1.5. We're just kind of estimating. And then there's a jump discontinuity at, let's say, 2.5. So that's all three types of discontinuity: infinite, hole, removable, and jump. Okay, so we're looking for an interval that doesn't contain any of these points. So notice this first interval that contains 0.5, right? 0.5 is between -1 and 1, so it's not that. The next one contains 1.5, so it's not that. The next one contains 2.5, so it's not that. So it ends up being D. Okay, so that's it. So if you want to know on which interval is a function continuous, if they give you a bunch of intervals as options, I would find the points of discontinuity first, and then find the interval that doesn't contain any of these points of discontinuity. So. Okay, for number 5, they say the function f is continuous on the interval from -1 to 3 exclusive, and is not continuous on the interval from -1 to 3 inclusive. Which of the following could not be the expression for f of x? Okay, so that means if it's continuous everywhere between -1 and 3, but not continuous when you include -1 and 3, that means it's either not continuous, it's continuous everywhere, it still has to be continuous from between -1 and 3, but that means it's not continuous either at -1 or at -3 or both. And they say which of the following could it not be? So you can see like the first one for A is not continuous. X can't be 3, so it's not continuous at 3. That's an endpoint. The next one is not continuous at -1. X can't be -1. The bottom, D can't be either one. X can't be -1 or 3. And so C is the only one that couldn't be the expression, because that's really continuous everywhere. That's not continuous on that interval. So that's C. Okay, next one, they said let G be the function defined above, where K is a constant. And they say for what value of K is G continuous at x equals -3. Okay. So, when they define these piecewise functions, they define it to be a certain function when x doesn't equal a number, and then, just a single number when x does equal a number. So basically the piecewise function is this everywhere except at a single point. So this g of x is really this function primarily, but just at one little point it's something different than this. Okay, so we want to know what value of k will make g continuous at x equals -3. So this is one where this must have a hole in it, and then at x equals -3, and then we'll fill in that hole with a certain y value that'll bring that point into the hole. Okay, so the way to do it is look at the function factor the top and bottom. Okay, and then we'll cancel the bottom and the top with that common factor. We realize still x can't be -3. Okay. So all you do to fill in that hole is really just plug in -3 into this simplified version. So if you do, so just make k equal to -3 minus 3 over 4. It's -6 over 4, and that's -3 over 2. Okay, so that's B. Okay, so another one of these. Let f be a function defined above for what value of c, if any, is f continuous at x equals 3. Okay, the fact that D is an answer choice where there's no such c, that means we have to make sure that there is a hole first, by looking at when x is less than 3 and when x is greater than 3. Make sure that those two pieces meet from the left and right, or are able to meet for some value of c. And then they have to not only meet, but they have to meet at 7, right, where the point is. Okay, so really just this, there has to be a value of c that makes this equal to 7 when you plug in 3 for x, or when you take the limit as x approaches 3 from the left of this, there has to be a value of c that makes that 7. And then when you take limit as x approaches 3 from the right of this, there has to be a value of c that makes this 7. And then in that case it'll be continuous. But and it has to be the same value of c that makes this 7, and that makes that 7. So let's see if there is one. I'm going to do the bottom first because the tops are quadratic, so we might get more than one. Oh no, we won't actually. Never mind. Actually, let's do top first. So I'll do formal work just to, that we're supposed to learn from these problems. So I'll do a little more than you'll have to do when you actually, if you were going to solve this problem. So let's say we're doing limit as x approaches 3 from the left. Okay, and then that'll be of whoops. So that'll be just plugging in 3 into that. So that'll be really c plus 3c minus 9. Okay, and then that has to equal 7. So 4c equals 16. Add the 9 to the other side, and that means this c would equal 4. Okay, and then I'm going to just do the shortcut. So let's plug in 4 for c, and then 3 for x, and see if we get 7. If not, then there is no value of c. Okay, so it's 2 times 4. Make sure I did that right. Yeah. Okay, so 2 times 4 plus 3 all over 3 minus 2. That's 8 plus 3, and that's 11. So that just kind of didn't work, There's only one value of c that made this 7, or made the top 7, sorry. That same value of c didn't make the bottom 7, so there's no value of c that makes the top and bottom 7. So we could have solved for some value of c that made the bottom 7, but that value of c wouldn't have made the top 7 because we know that there's only one value of c, and that's 4. So okay, so no value of c in this case. Okay, next one, they say let h be defined by h of x equals x squared minus 7 over x minus 3. Which of the following statements must be true? Okay, so sometimes with these multiple choice questions, it's good to just look at all the answer choices to see what they're even kind of getting at, what they're even focusing on. So notice every single problem, every single answer choice is x approaching a number from the left or from the right, the same number, 3, and then equaling infinity or negative infinity. So they're really dealing with talking about vertical asymptotes in this case. So anytime x approaches a number from the left or right and it equals infinity or negative infinity, then x equals that number that x is approaching is a vertical asymptote. So we can see by this is a rational function, and 3 makes the bottom 0 but doesn't make the top 0. You know, if you plug in 3, you get a number over 0. So that's definitely going to be a vertical asymptote. We just got to figure out what it approaches. Does it approach negative infinity or positive infinity from the left and right? Okay, so let's do that, and we'll do like a little trick, I guess, kind of. So let's say we do limit as x approaches 3. We'll say from the left first. Okay, so from the left means from values a little less than 3. So it's approaching 3 from values less than 3. So think about if you plug in values less than 3 for both of these x's. So the bottom, if you plug in values less than 3 into x, so you know 2.9 and then 2.99, 2.999, you know, values that get closer and closer to 3 but less than 3, then this bottom will always be negative. And then the top, you're plugging in just values closer and closer to 3, so this whole thing will get closer and closer to 2, but it's really just always a positive. Top's always positive for values close to 3. And then a negative divided by, positive divided by negative is a negative, so that's negative infinity. Okay, we'll do the same thing from the right. Okay, if you plug in values a little bit more than 3, 3.0 or 3.1, 3.01, 3.001, the bottom is always positive, right? The bottom is always a little bit bigger than 3, and when you subtract 3, that's going to be positive. And then the top is going to be positive for the same reason it was positive in the other one, because you're just plugging in values close to 3, and that's going to be somewhere close to 2. For the numerator, but still positive, and so that'll approach positive infinity. Positive divided by positive is a positive, so that's going to be positive infinity. Okay, so now left is negative, right is positive. Yeah, so that's C. Okay, so that's it for that page. So number 9, they say let f be the function such that limit as x approaches 5 from the left equals infinity. So right away, we're talking about a vertical asymptote at x equals 5. Which of the following must be true? And that happens to be one of the answer choices. So C says the graph of f has a vertical asymptote at x equals 5. So that's it. So this is the definition of a vertical asymptote. So, okay, next one. Okay, let f be a function of x. They say limit as x approaches 2 from the left equals positive infinity. So there's a vertical asymptote at x equals 2, and it's going up from the left. Right, from the left of 2, it's going up, and then also from the right of 2, it's going down. So we're looking for one that has a vertical asymptote, and that's B. That's going up from the left of 2 and down from the right of 2. Okay, and that's kind of one way to see, like when a function equals, when they say it equals positive infinity, they're just saying it's going up forever. And when it equals negative infinity, they're just saying it goes down forever. That's really all it means. It means the exact same thing. So, okay, so what do we say, B? Okay, next one. Let f be the function defined by f of x equals 2x plus 3 over x plus 1. Which of the following statements are true? Okay, so we just go one by one. First two talk about horizontal asymptotes. So let's see. So the graph of f has a horizontal asymptote of y equals 2 because limit as x approaches infinity equals 2. Okay, first off, we know it has a horizontal asymptote at x equals 2 because of the top heavy, bottom heavy, same idea. So the degree is the same on the top and bottom, which is a degree of 1, biggest exponent in the top and bottom of x. And then the lead coefficients, the coefficients of the terms on the top and bottom that have the biggest exponent, which is really 2 and 1. And divide those, you get 2. So we know that there's a horizontal asymptote at 2. And then we know that for rational functions, division of two polynomials, it'll always be the same asymptote going both ways. You'll never have, for a rational function, you'll never have a certain horizontal asymptote going to the right and a different one going to the left. That can happen with some functions, but not rational functions. Okay, so we know that both of those two are true. Okay, last one is talking about a vertical asymptote at x equals -1. Okay, so there's definitely a vertical asymptote at -1 because -1 makes the bottom 0 but doesn't make the top 0. So let's see if it's because of the right reason. So they say because limit as x approaches -1 from the right is positive infinity. Okay, so let's do that trick. If you plug in -1 for x in the top, you get +1. So when x approaches -1 in the top approaches some positive number. Okay, and when x approaches -1 in the bottom from the right, this is approaching, x is -0.9, -0.99, -0.999. When you add 1 to it, that'll always be positive, getting closer to 0. So the bottom will always be positive, and so that'll approach positive divided by positive is a positive, so positive infinity, so that's true also. So this one has all three true. That's D. Okay, next one. Okay, so this is one that has context. So they say population on an island is modeled by P of t equals 6,000 over 40 plus 60 e to the negative 0.03 t, where t is greater than or equal to 0. For t is greater than or equal to 0, where P of t is the number of people on the island after t years. Okay, what's the limit as t approaches infinity of P of t? Okay, so let's look at this. Let's kind of blow this up. Okay, so exponential functions, kind of just looking at, say we're just kind of looking at this part on the bottom, that exponential function that contains the variable. So if you think about it, when this t, when that t goes to infinity here, this exponent really goes to negative infinity. Because think about when that t is 1,000,000 or 1,000,000,000, you're multiplying it by a negative number, so it's going to be, kind of -1,000,000, -1,000,000,000, a little bit less since you're times it by 0.03, but really this exponent is really going to negative infinity. And so when an exponential, as long as the base is bigger than 1, which e's 2.7 something, as long as the base is bigger than 1, if the exponent goes to negative infinity, then the whole exponential goes to 0. So if we did limit t approaches infinity, then we know that when we apply the limit to this, and we can even use properties technically, we can apply the limit to the top and bottom, and then we can distribute it to each of these terms, and then we can pull out this constant, and then just evaluate it. Really, we just end up evaluating the limit of this exponential, the part that contains our variable, and then whatever this equals, we'll just kind of almost substitute it into this expression. So, okay, so really, we realize this exponential will equal 0. So this is going to be 6,040 plus 60 times 0, and then just simplify that. It's 150. Okay, they say let f be the function defined by f of x equals 3x to the 20th over 4e to the x plus 8x to the 20th for x positive. Okay, and that makes a big difference because exponentials behave a lot different when x goes to negative infinity, but in this case x can only go to positive infinity. And we want x to go to positive infinity because we want to find horizontal asymptotes. Okay, so we're only finding the one horizontal asymptote that goes to the right forever when x is positive, just because they kind of, that's their condition. So we'll look at that limit. X approaches infinity. Doing this to find horizontal asymptotes. Okay, so the big thing is this exponential in the bottom. So, you know, a lot of times you learn the top heavy, bottom heavy, same concept only for polynomials, but you can apply that to kind of any function that's a fraction. So first off, in the bottom, when x goes to infinity in the bottom, this exponential will at some point start to increase. Well, really at some point this term will be equal to this term, not for smaller values of x. For smaller values of x, since this exponent is pretty big, for smaller values of x, this term will be bigger than this term. But there's going to be a certain value of x where this exponential is the same as this, and then every value of x after that, this will stay bigger. And this will actually get bigger at some point way quicker than this will get bigger. And the idea is that this term, 8x to the 20th, will really become more and more insignificant compared to this term as x goes further and further to infinity. So that means that this term here doesn't matter. Okay, and then now when you have, you know, same idea, this term will be insignificant to this exponential down here. You know, the 3x to the 20th on top will be insignificant to this exponential on the bottom at some point. And so really this is bottom heavy, and so that's why this will equal 0. Okay, and if you have limit as x approaches infinity or negative infinity of a function equal to 0, that means y equals 0 is a horizontal asymptote. So definition, that's a definition of horizontal asymptote. Okay, next one, they say let f be a function such that f of 5 is less than 6, which is less than f of 7. Which of the following statements provides sufficient additional information to conclude that there is a value x equals c on the interval from 5 to 7 such that f of c equals 6? Okay, so hopefully you see that this is like an intermediate value theorem question, right? They're not asking for what's the value of c. For what value of c does the function equal 6? They're just saying to include that there is a value of c on the interval where the function equals 6. So this is just saying there's some c, some number in between 5 and 7, maybe equal to 5, maybe equal to 7. There's some x value on this interval where the function equals 6, just for some x value between 5 and 7. And that's the intermediate value theorem. So this is an intermediate value theorem type of question. Okay, and then the condition for that to be true, so first off, if 6 is between the y values of the endpoints of the interval, so right, 6 is between f of 5 and f of 7. That means as long as the function's continuous, which is a condition to use the IVT, then the function will equal 6 at some point in between 5 and 7. And another way to say that is let's say, I'll give a little example. So let's say that's 5 and that's 7. Okay, so let's say f of 5 is down here. Okay, let's say f of 7 is up here. Okay, and in order to satisfy this, that means that 6 has to be somewhere in between f of 5 and f of 7. Okay, so let's just say 6 is right here. Right. So the function, so that means there's kind of 2 points. So f of 5, 5 comma f of 5 is there, so that's a point on the function. And then 7 comma f of 7 is up here. So these are just these 2 points on the function. So if the function's continuous, it has to pass through this line y equals 6 somewhere on this interval, and that's what the IVT says. So the function has to equal 6, has to pass through this line y equals 6 at some point on this interval. But that only happens if f is continuous. If it wasn't continuous, it could come here and then skip over 6 and then go here, But if it's continuous, it has to pass through 6. Okay, last one, they say, let f be a function of x. Which of the following statements, if true, would guarantee that there's a number c in the interval from -2 to 3 such that f of c equals 10? Okay, so real similar to 14. They don't ask you for the value of c where the function equals 10. They just said, is there a value of c? Or, which of the following statements, if true, would guarantee that there is a value of c without caring what that value is necessarily. Okay, such that f of c equals 10. So this is another intermediate value theorem type question. Okay, so we kind of have an idea that we're dealing with the function being continuous on the interval. So let's look at C and D first and see if one of those is the answer. So actually, even before we do that, do you notice if whatever f of -2 is and f of 3 is, as long as 10 is in between that and the function's continuous, then the function will equal 10 at some point on this interval. So really, we just want to pick the answer choice where 10 is in between the y values at 2 and 3, -2 and 3. And so that's C, so we can see that's C. So notice here, D, they say it's continuous. That's good. That lets us use the intermediate value theorem. But notice the y values at the endpoints, the y values at -2 and 3, don't contain 10. 10's not in between 15 and 30. So, in this case, the function would have to, could equal any value between 15 and 30, but it doesn't have to equal 10 since 10's not in that interval. So, okay, so that's everything.